Alright gang, here we go. So this is Chem 2, Unit 3. We're going to be talking about empirical molecular formulas and combustion analysis. So this is a pretty math-heavy part here. The rest of this chapter really kind of is. So make sure that you're paying attention, do lots of practice problems. If you don't understand what you're doing, make sure you ask for help, alright? So determining empirical formulas. So remember, empirical formulas are the formulas that have the lowest whole number ratio, right? Lowest whole number ratio. Okay, so that's important. So we're going to be finding that lowest whole number ratio. Okay, a lot of times when you start these, you're going to be given the mass percent or the percent mass. So then we talked about how to find percent composition earlier in the previous video. Okay, so anyway, so a lot of times you'll start with that data, and you're essentially working backwards from what we did before. All right. Now there's a cool poem that you can memorize to help you out with these things. All right. So here, this is what you should be memorizing. You ready? So it's percent to mass, mass to mole, divide by small m, and then multiply till whole. Okay, percent to mass, mass to mole, divide by small, multiply till whole. Okay, so that walks you through the steps that you need to do. All right, so let's try one. All right, determining empirical formulas and examples. So we start with this guy, para-aminobenzoic acid. It's in sunscreen. All right, its carbon content is 61.31%, hydrogen is 5.14%, nitrogen is 10.21%, and oxygen is 23.33%. Okay, so we got to find the empirical formula. First step, percent to mass. So all we have to do for percent to mass is we're just going to assume that we have 100 grams of whatever it is that we're talking about. So assume you have 100 grams. So this percentage is just going to turn into a gram. This percentage is just a gram. This is a percentage is gram. Because if we assume we have 100%, then we have to assume that we have exactly 100 grams. Okay, that all these guys are going to add up to 100. So we just rewrite those and change the percentages to grams. Step 1 complete. Step number 2 is mass to mole. So all we have to do is use the molar mass, the atomic mass, for each of these elements to convert them into their relative moles. Okay, so the 61.31 grams of carbon divided by 12.01, you get that guy there. And so these are the moles that you get. Okay, go ahead and pause the video and check, make sure that I did it all correctly. Okay, see if you get the same answers. Okay, so that's percent to mass, and then mass to mole. Now we divide by small. So what that means is we take the smallest of these mole values and we're going to divide them into all the rest of them. So the nitrogen one, this is our smallest one. So we'll take 5.105 divided by 0.7288. Then we'll take 5.09 divided by 0.7288, and we'll take 0.7288, etc., etc., right? So once you do that, this is what you get. So you divide them and you see what number you get. Now, if it's really close to a whole number, you can go ahead and round it up. So 7.005 is really close, so you can go ahead and round it up to a 7. 6.984, round it up to a 7. 1.000, that's obviously what you're going to get because you're dividing a number by itself. And then down here, this becomes 2.001, close enough to a 2. All right, so we don't have to multiply to the whole. So we divided by small. The last step is multiply to the whole. Since we have all whole numbers, all of these guys are whole numbers, we don't have to worry about multiplying to the whole. All right, but so like say you ended with like a 0.5, you would have to multiply it by 2. If you ended with like a 0.3, like a 0.33, you'd multiply it by 3, you know, so on and so forth. So a 0.4 would be times a 5, all right, so on and so forth. Okay, so because these are all whole numbers, those whole numbers you just got are the subscripts. So this carbon was 7, so we get C7. That hydrogen was also 7, so we get H7, and then NO2. All right, C7H7NO2. Okay, let's do a practice problem together. All right, here we go. All right. A 2.144 gram sample of phosgene, a compound used as chemical warfare agent in World War I, contains 0.260 grams of carbon, 0.347 grams of oxygen, and 1.537 grams of chlorine. What is the empirical formula? All right, so we go percent to mass. Well, we've already got masses, so we don't have to worry about that. So now we go masses to moles. So we'll say 0.260 grams of carbon. and 0.347 grams of oxygen, and 1.537 grams of chlorine. All right. So now we're going to convert it to moles. So we'll put grams of carbon in the bottom, moles of carbon in the top. All right. And then same thing for oxygen. Grams of oxygen goes down here, moles of oxygen goes up here, and then one more. All right, grams of chlorine and moles of chlorine. All right. So now we just have to plug in our molar masses. So carbon is 12.01 to 1, 16.00 to 1, and 35.45 to 1. All right. Okay, so now we see what we get from all these. So we'll take 0.260 divided by 12.01, and I got 0.2165. So when you're doing this, it's helpful not to round too early, okay? 0.02, so 0.021649. 21. My goodness, I can't see my calculator. 1649. All right, so that's in moles of carbon. All right. Now we do the same thing with oxygen, and we say 0.347 divided by 16, and we get essentially the same number, so 0.021688 moles of oxygen. And then for chlorine, we'll take 1.537 divided by 35.45, 0.537, so we get 0.04336 moles of chlorine. All right, so that's, now we've gone mass to mole, then we divide by small. Well, which one's the smallest? Well, this one's the smallest, so we'll divide them all by 0.021649, divide this one by 0.021649, and we'll divide this one by 0.021649. All right, so this one's obviously going to equal 1 because it's the smallest. This guy here, this is going to be really, really close to 1, so we can just assume that's 1. For the last one, we'll just go ahead and type it out because it might turn out funny. Nope, so this is 2.003, so that just becomes 2. So we've got 1 carbon, 1 oxygen, and Cl2. So phosgene is COCl2 is the empirical formula. All right, pretty awesome stuff. All right, now the molecular formula. So remember that the molecular formula tells you exactly how it actually appears in nature, okay, in real life. However, and it's important to remember that it's always a multiple of the numbers in the empirical formula. Okay, it's a multiple of the number of atoms in the empirical formula. So it's always you're going to be able to take those subscripts and multiply them by some whole number to get the molecular formula, be it 1 or 2 or 5 or 500 or whatever. Okay, so once you find, in order to find the molecular formula, you need to find the empirical formula first, always. So if you have a problem and it says, find the molecular formula, the first step is to find the empirical formula. Once you find the empirical formula, you find the empirical formula weight. Okay, so you take, so the last one we had COCl2, okay, and you're just going to find the formula weight of that. So you'd be like 1 carbon plus 1 oxygen plus 2 chlorines, right? And add those guys up, right? So it'd be 12.01 and 16 and 35.45 times 2. Okay, so you find the empirical formula weight, and then you just take the molar mass of whatever it is, and this number has to be given to you. You take the molar mass given and divide it by whatever you get for the empirical formula weight, and then that's the number that you multiply. Okay. Easy peasy. So like in this example here, there was some compound and it was CH was the empirical formula. So 1 carbon for every 1 hydrogen, or 1 hydrogen for every 1 carbon. And then it was found that it has a molar mass of 78 grams per mole. We want to find the molecular formula. Well, first we need to find the formula weight of the compound. So CH, so that'd be 1 times 12 plus 1 times 1 because of carbon and hydrogen. We get 13 Okay, and then, so that's the empirical formula weight, so we'll call that EFW, and we're going to divide that into the molar mass given, so that's the 78. So we'll take the 78 divided by the 13, and we get this number 6. So that means that we need to multiply each of our subscripts by 6. So it was C1H1, so now it becomes C6H6. Okay. All right. Let's do this guy here. All right. Okay. All right, here we go. So we got cyclohexane. All right. So we've got 85.6% carbon and 14.4% hydrogen, and they give us the molar mass right here. So it's only got carbons and hydrogens, which is nice. So it's a little easier to do the empirical formula. So first step, percent to mass. So we just write the same numbers down, but just instead of writing percentages, we're just going to write grams. Nailed it. If anybody misses this step, you're in trouble. Okay, 14.4 grams of hydrogen. All right, now, so that was percent to mass. Now we go mass to mole. All right, so we go mass, so we go grams of carbon, and then moles of carbon. All right, 1, and then 12.01 grams, and then 1.01 grams of hydrogen for every 1 mole of hydrogen. All right. So percent to mass, so we say 85.6 divided by 12.01, and I got 7.1274 moles of carbon. Then we take 14.4 divided by 1.01. We get 14.257. 14.257 moles. All right, so that's percent to mass, then mass to mole. Now we divide by small. This one's the small one, so we'll divide by 274, and divide this one by 7.1274. All right, so this divided by that is just going to be 1 mole carbon. Or really it's a ratio, so moles cancel, so it's just 1. Sorry about that. And then right here we'll take the 14.257 divided by 7.1274. We get 2.00000. 2.000. Okay, so that means we've got 1 carbon for 2 hydrogens. So the empirical formula is CH2. All right, but it asks for the molecular formula. So they give us the molecular formula, the molar mass right here, 84.2. So we need to find the empirical formula. So we have the empirical formula weight. We have 1 carbon, 2 hydrogens. All right. So carbon is 12.01, and we have 2 hydrogens, so that's 2 times 1.01. So we get 14.03. Cool. So now all we have to do is take the 84.2 divided by the 14.03, and that's it. So 84.2 divided by 14.03, and we get 6.001. So that means we're going to multiply each of our subscripts by 6. Okay, so that means our compound is C6H12. All right, so that's the molecular formula for cyclohexane. Okay, and that's answer D then. We found a good one. Good job, gang. All right, now here's where the rubber meets the road. So this is called combustion analysis. Now the idea is you're going to take some sort of hydrocarbon, okay, and the sample. So this sample here that they're talking about is a hydrocarbon. So you take a hydrocarbon, and you're going to stick it in here into a furnace with oxygen. Lots and lots and lots and lots and lots of oxygen. So it burns. Remember, if you take any sort of hydrocarbon, so we'll say CXHYOZ, it can have nitrogen and other stuff, but essentially combustion analysis that we're doing only has these 3. And you react it with oxygen. Remember, you're always going to get the same 2 products. Now you get CO2 and H2O. Now, one thing to remember is this, you only get carbon dioxide and water if it is a complete combustion. If you have an incomplete reaction, that means this did not have enough oxygen to react completely, and so you end up getting a couple of other products. You get carbon solid like soot, and then some carbon monoxide. All right, no good. Okay, but we're gonna plug in a ton of oxygen into our furnace here to make sure that there's no possible way we're gonna have any sort of incomplete reaction. Okay. So anyway, so tons and tons of oxygen, so we get a complete reaction, complete combustion of whatever our hydrocarbon was. All right, so we plug in some hydrocarbon. We don't know what it is. We plug it in the furnace, and then the products get put through two different substances. One absorbs water, okay, and one absorbs carbon dioxide. Now the way it works is that the primary difference between water and carbon dioxide is the fact that water is polar, carbon dioxide is not. Water, remember, has a bent shape like this, with these lone pairs sticking up, and then carbon dioxide has like this double bonded O, like this, sticking off like this. Yeah. So anyway, so you get water and then carbon dioxide. So this guy will absorb the water and this guy will absorb the carbon dioxide, and you measure how much mass changed when you absorbed water and then how much the mass changed when you absorbed carbon dioxide. Based on that, those two masses, you can use the mass of carbon dioxide to figure out the mass of the carbon that was in your sample, and use the mass of the water to figure out the mass of hydrogen that was in your sample. Okay, because you know that the only source of carbon and hydrogen in your combustion was from your hydrocarbon, the CHO thing, whatever it is. So if you can figure out the mass of the carbon you produced over here, then you can assume that all of that carbon came from this guy right here. All right, and then same goes with the hydrogen. The only place the hydrogen could have gone was to form that water, so the mass of whatever water you get at the end is the mass of the water you started with. Now oxygen is totally different, because the oxygen, not only does it go into two places, but it also, we're feeding tons and tons of oxygen. So the real problem here is trying to figure out how much oxygen we have, and the way you do that is by you have to know the mass of what you started with, and then you subtract out the mass of the carbon and the mass of the hydrogen, and then whatever's left is the mass of the oxygen that was left. All right. So we're going to do a practice problem here in a second. All right. Yeah, you can go ahead and pause the video and take notes over these two slides right there. Okay. Kind of walking you through stuff. Here we go. Here we go. Here we go. All right. So the compound dioxane, which is used as a solvent in various industrial processes, is composed of carbon, hydrogen, and oxygen. Okay, it says combustion of a 2.203 gram sample of this compound produces 4.401 grams of carbon dioxide and 1.802 grams of water. And then it says that its molar mass, they found its molar mass to be 88.1 grams per mole. All right, so we need to figure out what the molecular formula is for dioxane, given all this information. So the first thing we need to do is figure out how much carbon we got to start with in our sample, and how much hydrogen we had in our sample. Okay, so we're going to start with our carbon dioxide, so 4.401 grams of CO2, and we're going to convert this to grams of carbon. So first we have to go to moles. All right, so there's our grams, so we'll put grams of carbon dioxide, and for every 1 mole, so we need the molar mass of carbon dioxide. I'll do that up here. So carbon dioxide has 1 carbon and 2 oxygens. All right, so carbon is 12.01, oxygen is 16, so 2 times 16.00. Now, so 32 plus 12 is 44.01. All right, so that's the molar mass of carbon dioxide, 44.01 grams of carbon dioxide. Okay, now we have to convert to moles of carbon. Okay, so we'll put moles of CO2 down here, and then moles of carbon up here. Okay, now inside carbon dioxide there's just 1 carbon, so we put 1 and 1. All right, now we have to go to grams of carbon, because well, let's stop there for a second. We actually need that mole of carbon later, so we're going to stop our equation there and just do that math real quick. All right, so we need that moles of carbon when we're doing the empirical formula, so we're going to stop there. All right, so we'll just take 4.401 divided by 44.1. Isn't it nice how this worked out? So the answer is just be 0.1 moles of carbon. All right, 0.1 moles of carbon. Now we have to figure out the mass, though. So we'll say for every 1 mole of carbon, we have 12.01 grams of carbon. So this becomes 1.201 grams of carbon. All right, so that's how many grams of carbon our original sample had to have had. All right, now with water, we have 1.802 grams of water. Okay, so we got to do the same steps. We got to convert it into moles of hydrogen first. So for every 1 mole of H2O, we have 18.02 grams of water. Okay. Now we have to think about this real quick. We're going to go from moles of water to moles of hydrogen. So moles of hydrogen go down here. All right, moles of hydrogen go up here. Moles of hydrogen go up here, moles of water go down here. So for every 1 mole of water, we have 2 moles of hydrogen. We know that because there's a subscript of 2. Okay, so we're going to multiply that out. So 1.802 divided by 18.02, well, that's 0.1. And then we multiply it by 2, so we get 0.2 moles of hydrogen. All right, now we need to figure out the mass of hydrogen. Well, we know that for every 1 mole of hydrogen, there's 1.01 grams of hydrogen. Okay. Now notice I'm not using the diatomic nature of hydrogen in any of these things, because in my hydrocarbon, hydrogen is not a diatom. It's stuck with other things, so it doesn't have that diatomic nature. So we take 0.2 times 1.01, and so we should get 0.202 grams of hydrogen. Let me just double check this. Times 1.01. Yep, 0.202 grams of hydrogen. Okay, so our original sample had 0.202 grams of hydrogen and 1.201 grams of carbon. Now we have to figure out, remember, so that's those two. So it had that much carbon, that much hydrogen, but we need to figure out how much oxygen it had as well. Okay, so we know that our total sample was 2.203. So if we take the 2.203 gram total and subtract out the 2 masses that we got here, we know whatever's left over had to have been the mass of oxygen, 0.202. All right, so we'll take 2.203 minus quantity 1.201 plus 0.202. And so that means there was 0.8 grams. All right, and then we go to the thousandths place, hundreds, no, tenths, hundredths, yeah, thousandths, 0.0800 grams of oxygen. All right, so in our substance there was 0.800 grams of oxygen, but, all right, so that's all fine and dandy. We now know the masses of carbon, hydrogen, and oxygen. But remember, our idea, we need to get to the molecular formula. All right, that's what we're after. So now we need the molecular formula. Well, the first thing that we need to do is find the empirical formula. Remember, whenever you find the molecular formula, you always have to find the empirical formula first. So that means we got to use our poem. All right, so percent to mass. Okay, we don't have any percents, we're good to go. And then mass to moles. Okay, so we got to convert all our masses to moles. Well, that's why I had us do this earlier, right? So we already have these moles. Awesome. So 0.1 mole of carbon, 0.2 moles of hydrogen, and now we need the moles of oxygen. So we'll use this value up here. So we're going to convert that to oxygen here, or moles of oxygen. So we'll put grams of oxygen in the bottom for every 1 mole of oxygen. So that's 16.00 grams of oxygen. So 0.8 divided by 16 divided by 16, it's like 0.05. See, it's a good thing I plugged in my calculator. 0.05 moles of oxygen. All right, so we'll plug that down here. 0.05 moles of oxygen. All right, now so that we've gone percent to mass, mass to mole. Now we got to divide by small. So we're going to divide each of these by the smallest. Maybe I need to rewrite this so it's like a little easier to see what's going on. All right, pointer, pen. All right, so let's see if I can write it a little better. So 0.1 moles of carbon, 0.2 moles of hydrogen, and 0.05 moles of oxygen. All right, divide by small. Oxygens are small, so we're going to divide each of them by 0.05. All right, so that's going to be 1. We're going to divide this guy by 0.05. All right, and that's going to be, so 0.2 divided by 0.05, so that's 4. I guess I could have done that in my head. That's embarrassing. So that's 4. And then we can divide this guy by 0.05. All right, and so that's going to be 2. So our empirical formula is C2H4O. That's the empirical formula. Now we have to find the molecular formula. This problem just doesn't end, does it? So we need to find the molecular formula. All right, well, in order to find the molecular formula, we need to find the empirical formula weight. All right, so we got 2 carbons. we have 4 hydrogens, and we have 1 oxygen. All right. So we have 2 times 12.01 and 4 times 1.01 and 16.00. All right. 12.01 times 2 plus 4.04 plus 16. You get 44.08. I guess that's right, 44.08. All right. So that's the empirical formula weight. All right, we're going to label that empirical formula weight. Okay. Now we need to find them. Now we just take the molar mass they gave us, 88.1, and divide it by the empirical formula weight that we found. So 88.1 divided by 44.08, and we obviously get something really, really close to 2, or a squiggly line, the weirdest 2 I've ever drawn in my entire life. So 2, and so that means we multiply all the subscripts by 2, so our C2H4O becomes C4H8O2. So that is the empirical formula, or the molecular formula for dioxane. Combustion analysis. It's intense and it's really long, and you have all the tools that you need to solve it, but you just got to keep track of where you are. All right. So remember, so you're going to convert it to moles of carbon and hydrogen, then convert those to the masses, subtract it from the total to find the mass of oxygen, then take the oxygen in moles, then from there you can figure out the empirical formula, and then from there you can figure out the empirical formula weight, divide it into the molar mass, and then figure out what to multiply all your subscripts by, and you're good to go. So that is the end of it for this video, combustion analysis. Hope you had lots of fun. I'll erase this so you can kind of see what's going on. Anyway, so let me know if you have any questions. You got a quiz coming up. I know you can do it. I'll talk to you later. Bye.